Hello, we are Team 6 for the University of Nevada, Reno ChE 415 design project. We'll be focusing on granular activated carbon water filtration system. 1 in 10 people across the world lack access to safe drinking water. This leads to nearly 1.6 million deaths per year from poor sanitation. In the U.S. market, granular activated carbon is roughly $6 per pound, which makes it an inefficient mean in the industrial application, but it could be used to filter your own private water source. To get a good idea, the team decided to pull and test water out of Manzanita Lake from the UNR campus. Here are the dimensions and measurements of our filter body. Hello, my name is Ian. I will be speaking to you about how the water filter actually works. We start with dirty water on top that flows into our filter body, which is composed of rocks on top, activated carbon in the middle, and cloth on bottom to hold everything inside the filter. This then flows into our collection bucket, which is where we will get the water to do our TSS and TDS testing. Over the course of about an hour, we will also be measuring flow rate to get an idea of how much is actually being absorbed and collected inside the carbon itself. The team used 250 grams of activated carbon for each run during the filtration process. The equations used throughout this project to solve for porosity or flow rate will be given towards the end of the video during the result interpretation section. In this section, we will be talking about the equations that the team used during the course of the entire project. The first is superficial velocity, which is calculated by the flow rate divided by the cross-sectional area of the filter body. The next is porosity, which we calculated to be 0.66 from the equation that is shown. Next is the Ergen equation, which the team used to calculate friction loss inside of the filter body. The flow rate was calculated to be laminar, so this became just the first half of the equation, which is shown here. Lastly, the team used this mechanical energy balance because it relates potential energy, kinetic energy, change in pressure, and the friction loss, which is all found inside of the filter. The pattern in the volumetric flow rate versus volume filtered was exactly as the team expected. The downward trend is due to the particulate buildup in the activated carbon filter. Unfortunately, not all of the data that the team gathered was as useful as volumetric flow rate through the filter. Some of the places in this measurement seem to imply that the carbon filter actually added solids to the Manzanita Lake water. It's highly unlikely, but the general downward trend indicating decrease in performance and buildup of solids as the filter time progresses was completely expected. The decrease in porosity over the life of the filter was to be expected as the pores are becoming filled with all the sediment that comes from the lake water. Unfortunately, many of the total dissolved solid concentration values were found to be impossible by the team and were discarded from the project, so that left this section of those tests inconclusive. After calculations and considerations, the team did find that this project was an overall success even with the loss of the total dissolved solids testing. Overall, the values and the trends that the team calculated were expected and did match the values and the trends that have been set by the activated carbon industry. Due to the high cost of activated carbon in large amounts, this would not be a great option for the industrial scale, but it would be a good option for disaster when drinking water is scarce and it could be given out person to person. Team 6 would like to thank Professor Cornella for the opportunity, the UNR Chemical Engineering Department, the UNR Environmental Engineering Department for the lab use. Questions, comments, and recommendations are always welcome.